The answer to the second question is closed. We start in the closed state. Then the user program calls connect, and we transition to the send state. While in the send state, the user program calls close. So there's an edge from send on the close event back to the close state. So now our sockets are in the established state. They're exchanging data. The 6 states in blue boxes are how TCP tears down a connection, or how it closes it. It's sometimes useful to talk about tearing down a connection because the word close means something in terms of system calls. A connection exists after one side closes it, as we'll see. There's symmetry between how TCP sets up a connection and how it tears it down. Where connection establishment uses synchronization or SYN packets, connection teardown uses finish or FIN packets. If one of the sides of the connection calls close, it traverses along the right edge on the left to the FIN wait 1 state. This causes it to send a FIN packet to the other side of the connection. This is called the active closer because it starts the operation. The other side receives the FIN and takes the blue edge on the right to the close wait state. It remains in this state until the program inside calls close, at which point it sends a FIN. Here's where it gets a little complicated. A TCP connection is bidirectional. The active closer has closed its direction of the connection, so it can't write any more data. But it could be the passive closer has more data to send. So the passive closer can continue to send data, which the active closer receives and acknowledges. Or it could close its side of the connection too. Or it could even have decided to close the connection at the same time, such that we have 2 FIN packets crossing each other in the network. From the FIN wait 1 state, where the active closer is, there are 3 possible outcomes. First, the passive closer might acknowledge the FIN but not send a FIN. In this case, the passive closer is in the close wait state and can continue to send data. This is the lowermost edge, where the active closer enters the FIN wait 2 state. Second, the passive closer might close its side too, acknowledging the FIN and sending a FIN of its own. This is the middle edge to the time wait state. Finally, it could be that both sides actively close at almost the same time and send FINs to each other. In this case, both are in the FIN wait 1 state. Each one will see a FIN from the other side that doesn't act its own FIN. In this case, we transition to the closing state, and when our FIN is acknowledged, we transition to the time wait state, just as with the middle edge. TCP transitions from FIN wait 2 to time wait when we receive a FIN from the other side. It then stays in the time wait for a period of time until it can safely transition to close. The final blue edge, from last act to close, occurs when the passive closer's FIN is acknowledged. Now, on one hand, that's a lot of detail. There are 12 states covering lots of cases. But I hope you can see how this finite state machine makes what was previously a few colloquial descriptions and gives them detail and precision. Trying to implement a properly interoperating TCP based on those descriptions would be really hard. This diagram precisely specifies how TCP behaves, and so it's tremendously useful.